Alright, so this is the circuit that I'm going to be tinkering with. And it consists of two single transistor oscillators, low frequency one and audio one. The low frequency one is pulsing the LED, and as I've discovered is the duration of those pulses is so short that the camera's having a hard time picking up every single pulse. But rest assured, the audio is changing at the same rate as that LED is pulsing. And this is the basic circuit. No, this one is the basic circuit. You don't need, for oscillation, you don't need to have anything in it connected to the base. But what you do need is the transistors to have its collector and emitters reversed and an appropriate supply voltage. So, what I believe is happening here is that this circuit is exploiting the fact that the reverse breakdown voltage between the base and emitter is quite low, like the order of 5 or 6 volts. And many transistors are that low, including some very high voltage transistors. They are high voltage between the collector and base, but 5, 6, 7, I think one I'm going to test later has got 9 volts between that, between the base and emitter, and yet it has a 700 volt range on the collector to base. So, reverse breakdown is another way of talking about Zener-diodes. And so you could say that the device in its physical construction has an intrinsic or a parasitic Zener-diode in it. And when operated in this reverse active mode, that becomes important. And so what happens here is that I'm trickle charging this 47 microfarad through this 100 kΩ resistor, and as it hits a particular threshold, this switches on, and because of that Zener-diode current to the base, it switches on quite hard. So it's going to discharge quite a lot of the charge in the 47 microfarad capacitor through the LED, causing not only a bright but very short-lived pulse. The 100 kΩ resistor that I've got here, that I'm trickle charging that's pretty much on the cusp of operation of these transistors. I'm using BC547s, or in fact, I think on the low frequency one I've got a 546 at the moment. And the reverse breakdown voltage on those, I think they're both 5 or 6 volts. I'll insert the data sheet and have a bit of a squeeze at that. Now the important point here is that as the voltage at the emitter approaches that threshold voltage, it starts to leak current. And the problem here with having a high resistance is that that leakage current, as it's approaching threshold, can prevent this 47 microfarad capacitor from charging up to the point of reaching that threshold, so the transistor doesn't switch on hard, which is what we need in this particular circuit. So the simple response to that is to lower that resistance and then deal with the consequences of either having more current draw from the supplying circuit and or having to increase the size of the capacitor there. On the audio side, it's basically the same circuit, just the transistors being flipped around for convenience of connection between the bases. But yeah, likewise, if you don't have that, that's the audio circuit, but it does look different. And let me go back to one of the earlier designs from the 80s, which I'll show the article for soon, but essentially that's the circuit, and that's the circuit I did try, and it does work. It does oscillate, produce an audio tone. So you notice here in the collector that it's just shorted straight to ground, so it's literally shorting out that 0.1 microfarad capacitor. The problem I found though was that when I linked the bases this way, no matter how high or the range of resistance that I could add in here was very narrow and seemed to be unstable to the point that the oscillators would stop oscillating, and it was becoming difficult to sort of justify the behaviour of the circuitry. And then it became obvious that the advantage that I was looking at of discharging the 47 microfarad to give me my light pulse unbalanced the collectors, so that hooking the bases up this way was not was introducing the instability. So what I needed to do was to put a load, or make the collector circuits equivalent between the two. What I did obviously would be to put an LED in there as well, and I did try that, but it worked. But I decided that I needed something different. I didn't want to use another LED in there for no particular reason. So, I didn't want to use another LED. So I eventually stumbled upon this addition to the collector circuit. So I originally started off with a 1K resistor, and it would not oscillate. And I literally stumbled on the fact that I could put a capacitor here in the collector circuit, and it would start to oscillate. Now the explanation goes along this lines, I believe. So we've got 2.1 microfarad capacitors, one in the emitter circuit, one in the collector circuit. When the one in the emitter circuit reaches the threshold, it switches on and dumps, because they're the same size, same capacitance, it dumps half of its charge into the lower one, and consequently the voltage halves. And in this particular case, that reduction in voltage at the emitter is enough to turn the transistor off. So it then begins to charge up again, and consequently goes through the process. Now obviously, if I did not have that 1K resistor there, I would expect it to continue to dump charge into that 0.1 microfarad capacitor until it can no longer, between the supply voltage and the voltage that's achieved at this point, he can no longer get enough threshold to switch on. I'm supplying this with 26 volts of that order at the moment. So by putting in that capacitor there, I'm going to discharge that and reduce the voltage. But this circuitry does affect the frequency, overall frequency of this audio oscillator. So this and this by itself do not set the frequency alone. It's the combination that sets the audio frequency. Okay, so this is an old book. I think it's around about the early or mid 80s, and the circuit in question is this one. And as you can probably see there, they call it a simple oscillator, and they start talking about a negative resistance region, yada yada yada, and they give us a trace, a transfer graph. So as the voltage between the emitter and collector goes up, the current goes up. Okay, so they're measuring across there. So as the voltage reaches a particular point, it starts to ramp up, and that's very similar to how a Zener diode works. And so, I mean, they talk about a negative resistance region. And they show an example of what the waveform is going to be there. And as you can see in here, they've actually got the load in the emitter, so the load itself is supplying the charge current for the oscillation. Okay, so going into examining this circuit, basically I've pulled everything out and I've only got the low frequency side. So I've got channel 1, which is the yellow trace there. That's hooked up to the emitter, and channel 2 I've got it on the collector just above the LED, using a different LED this time. Don't know whether that's going to make any difference to its visibility because it was a timing issue. So let's look at the oscilloscope. So what I've done is just to get a rough idea of, I've got it 2 volts per division on a 100 millisecond timescale when it doesn't want to go to sleep. So I've got my measurements up here. So on channel 1 I've got a minimum of 8.64 volts and a maximum of 10.48. And on channel 2 I've got a Vmax of 2.88 and a Vmin of 320 millivolts. Both of them have got the 0 set on the first division. So if we turn on cursors, manual cursors, that's already pre-set up. You can see that between cursor A, let's turn the right dial, between cursor A and B we've got a frequency of 1.95 Hertz. So we don't need to see the cursors anymore. And go back to our measurements. So, looking at our circuit again, what it's saying is that the voltage ramps up between the minimum of 8.64 volts to a maximum of 10.48 volts, at which point it switches on, turns on the LED, and then switches off very quickly. So if we look at those voltages, you'll see that the collector voltage is tracking the emitter voltage with a difference of, let's do the minimums, so basically 8.5 volts, 8.4 volts or so. Okay, so this is a different transistor. This is a BC546, which I didn't do any Zener measurements on. I think the previous one was a 547, and it had a Zener measurement of 8.10 volts, which you're not going to see in this video. So that's something to look forward to. Now, it switches on at this point, and because we're zoomed all the way out at 100 milliseconds per division, not only is it slow updating, you'll see it armed and triggered. If I zoom in, going the right way, you can see this is the switch on time. So it's reached that threshold, switches on, discharges the capacitor to this point and switches the transistor off. And you can see that reflected in the collector. It spikes up from from that point there, which won't be the minimum, up to that point there, which should be the maximum of 3.36 volts. discharges following that curve, at which point the transistor switches off, and then the residual charge, if there's any, bleeds off at this point. So where's the residual charge? There's no capacitor on the output, there's only the LED. So that's something that's interesting and might be worth investigating further. So on the time scales there, let's use cursors again, it's easier. I don't like to count off divisions when you've got cursors. Okay, so if we move cursor B, it's the easiest one to move. Let's call it there, cursor A. So after switch off is about 1.4 milliseconds. Okay, so we can measure the current directly flowing through the LED, and we can do that by putting in a sense resistor. So what I've done is I've inserted a 10 ohm resistor into the cathode circuit of the LED. So in essence, the circuitry, I've put a 10 ohm resistor in here in the cathode, and I've set up the oscilloscope with the channel 1 on the anode and channel 2 on the cathode. So the only thing we might need to know is what the actual resistance of that 5% resistor is, and so just measure between the ground and the resistor, and we get 10 ohms exactly. Yeah, it's a 5%, it's a gold band. So, how do you like that? Anyway. So let's apply power and we'll look at the results. Okay, what have we got? So straight away we can see we got a Vmax of 728 millivolts. Divide that by 10 rather, and we get 73 milliamps at its peak in the blue trace. And in the minimum, that cursor B is roughly at the point where it switches off, and so we've got 13 milliamps essentially. So it goes from a peak of 73 into 13. Just adjust that cursor. I should be able to go by the measurements there, but it doesn't hurt to get the cursors right. And while I'm at it, might as well get the cursor B down there. So with the new adjustments, we're at 72 milliamps and 10 milliamps. Okay, so that's using one of the newer yellow LEDs. So what I'm interested in, not only is in the current traces, what I'm interested in is these white LEDs, high intensity LEDs. The blue colouring there is me having written on there, so it is actually yellowish if you look in the centre, and that yellowishness is a phosphor coating. So I think most white LEDs achieve the white light through a phosphor action, and to me a phosphor means persistence, and persistence means the camera might be able to see the lead for longer. So I do know I've used white LEDs for strobes, so the persistence is not that long, but is it long enough to make a difference? Let's take a look. Let's whack him in. Whoa. And what's that done to our oscilloscope traces? So yeah, it's triggering, so it's definitely triggered. So, and the waveform's changing, and it's made no difference to the trace. So we're still drawing. So the cursor's exactly where they were before. So it didn't make a cracker of a difference in terms of, but the light intensity is much higher. Interesting. And so there's that little discharge trace there that we saw before, and you can see it's clearly after the current. So this must be some sort of capacitance of the transistor itself, and because the load is switched off, it's probably measurable in the picofarads, I would expect. Interesting. So another experiment we can do, I'm not sure how many of those flashes that we're seeing, is changing the capacitor. So that was a 47 microfarads. If we go to a 25 volt 100 microfarad capacitor, it should slow down the pulse rate, but does it? It does. So I didn't have the cursors on that, did I? So let's switch it to time. Yes. Let's measure. Sorry. Cursor B. We will move to the blue trailing. So we've got 4.24 milliseconds with 100 microfarad. And with the 47, should get the polarity right. And with the 47, we've got, so the duration of the pulse does increase with the capacitance to 2.2 microseconds. But the currents were the same, weren't they? I'm pretty sure the currents were the same. The starting and ending currents, they were about the same, weren't they? Yes, they are indeed. It's just that you got more charge, so you can see that the peak current's the same and the ending current's the same. It's just that because you've got more charge in the capacitor, it takes longer. I suppose that should be obvious, shouldn't it? Or is it? Let's try some other LEDs, white LEDs from a similar batch, I would expect, because they came out of the same device. Let's try this one. That initial light pulse is quite surprising. There you go. Aha, we have a difference in the peak current. So that's interesting. So there was that white, yellow and white LED had pretty much the same characteristics, yet another white LED from presumably the same batch has a differing peak current. So we can see there that the cursor A peak is different. I don't need to move the cursor actually. I can just look at the measurement because that's just your Vmax. Right, so and let's try a third white LED. that's lower yet again. So we got 69 milliamps, and the lower well, you could argue whether it's lower or not. I suppose it would be lower. Alright, once we have cursor around. Having the cursors means is that when I can see any differences regardless of what these readings are. So. And because obviously I'm not looking at the oscilloscope while I'm changing components. I'll see it when I play the video back, but and so there's virtually no change in the starting and ending currents of the LED from the rate there. That was 47. Oh, that's a point. What if I go to something like a 1 microfarad? Get a fast oscillation theory. Is it up here? Yeah, I can see some light there. Zero that. Yeah, there's certainly not a lot of pulsing going on there. The peaks have to go up one level. Look at that. So we've gone down to 100 millivolts. So cursor A. Going up to there, and cursor B is pretty much to 0. So 35 milliamps, stopping at 1.6 milliamps. And I've got a 4.7 somewhere. Yep, 4.7. Yep, 4.7. 25 volts. It's a 50 volt 1 microfarad. Okay. Interestingly enough, the peak current didn't change at that time. Well, a little bit's gone to 35 milliamps. You can have fun all day. So I think it's about time that we take a look at the voltages between the bases in this circuit. So I've got channel 1 plugged into the base on the low frequency oscillator, and channel 2 into the base of the audio frequency oscillator. So on the oscilloscope we can see I've got my FFT mode up, and the top trace has got a copy of the audio frequency at its base, which is shrinking and growing. So the FFT analysis of channel 2, you can see the harmonics of that particular waveform, which is sort of kind of sawtooth, and you can see the various harmonics there, but you can see that the frequencies are shifting there. It's probably the easiest way that I can think of to show you how that FFT, how the frequency is changing. But let's turn the math off and take a look at that. Now I'm triggering off channel 2. I change the trigger to channel 1 and set to trigger at the appropriate point. And we change that to channel 1 and then set the trigger up here somewhere like that. I can then show you how that amplitude is changing between the low frequency periods. It's better. So yeah, it's much easier to see now how the amplitude at the low frequencies base of the audio frequency is getting reduced, having its as it approaches the threshold for switching on, it starts absorbing current or something to that effect. So that's fundamentally how it operates. So what I've got in there currently is I've got the 500 kilo ohm resistor potentiometer in series with 100 k ohm. So without the effects, without the interaction, just pull 100k out. You can see how the low frequency one now doesn't have the audio frequency on it at all, and the if I set the trigger back to channel 2, and turn on cursors, you can see that the frequency is about 4.6 kilohertz. So another important aspect is the current consumption. So I just got that plugged into my meter with the true RMS switched on, and you can see it's just a fraction over 1.1 milliamps of current, giving me a flashing LED, etc. Could try one of the high intensity LEDs, but in theory it shouldn't make any difference, because it's the trickle charge current that's important here. So moving to a more efficient LED hasn't changed the burden current, the current that it's going to be drawing from the circuitry where it's going to be plugged into. So it's a pretty nice result without the piezo. Okay, so another aspect that could be important is the temperature on the frequency. So just got the oscilloscope set up to trigger off channel 1. There's a little trick with this particular oscilloscope is that the frequency that it measures is centered about where the trigger point is. So I can still be on DC and just move the trigger up to the appropriate point, and then the frequency will start to give me reasonably accurate results. So you can see there that the current consumption is just bordering on 1.1 milliamps. I've taken the warble away so that you can hear any frequency changes, and so ambient temperature's around about 28 degrees or so. Just hit it with a bit of freeze spray. So we're what, 4.4 and a half, whatever, 4.45 kilohertz. Drop down to 4.3. Frost it over, 4.3. Starting to recover. Back up again. You can just hear it coming up. And if I hit it with my soldering iron, which is set on its lowest range, about 150 degrees Celsius. Just drop that on the top, not the most appropriate point to put it, but that'll do. Is it coming up or not? A better way. Use some hot air on it now. There we go, 4.5. 0.6. 4.7. Come those down again. So that was a rather long introductory video to this warbling alarm. So next time I hope to take a few steps back, get an idea of my surroundings, and then start to zoom in on some of the details.